I'm Chad Van Tol. I'm accompanied by Stephen Don and Travis Steenwick. Our Capstone group expanded the University Control Network due to the construction of North Holland destroying some points. And I'll hand it off to Travis to start us out.
Alrighty, so our objective here was to expand the Ferris State University Control Network. And to do this, we had to figure out good spots to put these, and North Hall was a good location for this because there was some old points that got eliminated with the construction of that, and there's not a whole lot of control on the north end of the campus anymore. So you can go to the next slide. So our project overview is we're going to set we did set our concrete monuments around the north sector, Ferris State University. Once we had that done, we were going to we did a static observation of the monuments that we set and acquired Opus solutions. Then we manually adjusted these static observations to get our own solution, and then compare these solutions to see the difference between what we acquired manually and what we got from Opus. And we're also going to do a big rapids course station check. And then once we're done with all the staticking, run a digital level through our new control points and tie them into some of the existing control points that are on Ferris's campus. And then at the very end, we run a closed traverse throughout the network as a check. I'll go to the next one. This is our site, and down on the bottom right of the picture, you can see where the swan is. And then it has all the locations that we chose for our 5 new concrete monuments. Okay, you can go to the next one. So the equipment that we were going to use for this project was 8 dual frequency GNSS receivers. These receivers were equipped with 2-meter fixed height tripods. Then for the leveling, we used a digital level with the standard in-bar staff. And then to run the traverse, we used a robotic total station. This is a diagram of a control monument for MDOT specifications. We use this as a reference to what we were going to do for creating ours. As you can see in the diagram, at the top it shows that the specifications are 12 inches in diameter and 5 foot deep. For our project, we ended up having it be 4 foot and deep with 10 inches in diameter. Go to the next. So the next step here in the process was to set our monuments. In order to do that, we had to pick locations that would be good for these 5 monuments. Once we had the locations picked out, we then worked with the Ferris State grounds to have them locate any utilities that were in these locations. And once they did that, we were able to walk around and just double check and adjust our locations so that we wouldn't run into any utilities underground. After that, we then excavated the holes for these monuments using an auger and a post hole digger. So as you see in the picture, there is a top view of our monument after we set the cap into it. So we used 10-inch diameter by 4-foot sonotubes as forms. So put those down into our augered holes and then poured the concrete in. And then placed the cap into the wet concrete and then backfilled around it. And then we let it sit for a few weeks so that the concrete could cure up. And then once it cured for a while, we then were able to go in and stamp our monuments. Here is some pictures of 3 of our 5 monuments. One on the left is Van Tol, the one in the middle is Steenwick, and the one on the right is Don.
All right, for the static observations, the team developed a plan with SSI, being that we're going to use their equipment. We had to choose a weekend and get our static observations done. We used 7 of their GS15 dual receiver or dual frequency receivers and 1 GS16, and then we had 1 CS20 controller. Also, like Travis said earlier, we had 8 of their fixed height, 2-meter fixed height tripods. Oops. So once we got the equipment and the weekend plan where it worked for everybody, we were going to go through, and before setting up the static set, the GS15s, we were going to use the GS16, or we did use the GS16 to shoot in the monuments twice as a blunder detection. We did 10 epochs facing north and 10 epochs facing south to account for any rod error. And then, so like I said, we only had 7 of the GS15s, and so the last static setup, we used the GS16. And we also had 8 red brick batteries, big ones, so we could get the length of time we needed out of each static observation. Well, one of the issues we had with one was it was a little older and it wouldn't hold the charge. So when we went around, set up all of our static setups, we went back to check them, and we found that one was dead, within the hour. So we had to come up with a quick plan. Good thing we had a couple regular GPS controller batteries charged, so we were able to get 4 hours out of our last setup. That was the shortest one we had, was 4 hours. Our longest static observation was 8 hours long. So for the digital leveling aspect of this project, the plan was to first locate 2 first order class 2 NGS vertical control points. As you can see there, there are 2 CAPS NGS points. One's MDOT 54603. The other one was MDOT Big Rapids. So to start, we were going to run a level loop between the 2 NGS points to check and make sure that the elevations were correct as reported. And then starting at the MDOT 54603, which is near campus, we were going to then level through all of our points used in the static observation. Then after that main loop was done, we were then to run 2 redundancy loops just to check our previous observations on those points. Here's a picture of the planned level loops. The only one missing would be the one between the 2 NGS points, which NGS Monument MDOT Big Rapids is to the north of this map here. So due to COVID-19 pandemic, we were able to get the leveling part done in this project. To show that we had knowledge of running a digital level loop, the team ran a couple level loops on a major state highway construction site. The leveling there is pretty much the same as what we planned on our project, just different location. We started off an NGS monument, leveled through various benchmarks and control points within the project, and then closed out on another NGS monument. And once that checked out, we then ran a couple more loops through the project to establish elevations on many more control points and benchmarks to be used for that project. So for the traverse loop, after everything was, right. Well, so the plan was once the all of our measurements were adjusted and established, and we had final coordinates and elevations on our new NGS monuments. We were going to run a closed traverse loop to check and make sure our observations were good. Again, due to the COVID-19 pandemic, this could not happen because we didn't have any established elevations on our NGS points. The same thing, to show the knowledge of running a closed traverse loop, the team decided to shoot 4 points in around SSI's parking lot and Standish, and then run a closed level loop around them. The area of closure for this performed traverse loop was not the best, and this is because we only shot them in 20 epochs, each point 20 times. They didn't have hours of static observation like our points on campus. So we expected for the points on campus to have a much better closure. Okay, so for the NGS part of this project, we were going to fill out NGS data sheets for our new monuments. The NGS data sheets contain all information about the mark that you'll need. It contains information about the location, coordinates, elevation, when it was recovered last, description of the mark, everything you need to know about that mark. The plan was to fill out these NGS data sheets for the newly established monuments, but the team could not complete this, again, because of the epidemic or the pandemic, and the fact that there was no elevations established through digital leveling on these new points. As you can see here on the right, this is a picture of a mark recovery form through NGS. These mark recovery forms are to be used to update the NGS website about various marks. If you go to a mark and you recover it or it's usable, you fill out your information and describe the current physical state of that mark. And then for ours, obviously the points that were set around North Hall previously before it was built were destroyed during construction. After talking to John Ellingston from NGS, we were asking him about how to remove the data off of NGS's database. And it's not that simple. You can't just call and say, hey, I know this one's been removed. It's no longer there. It doesn't work like that. You actually have to send a picture to them, showing that the mark is removed from its described location. Because just in case they've had issues in the past where somebody goes out looking for a mark, they can't find it. They say it was destroyed, they remove it. Well, then somebody else goes, looks a little harder, digs a little deeper, and they find it, but now all the data is removed from the database. So they switch that up now. You actually have to send in pictures that it has been removed. And then next, we have types data sets, and so I'll hand it off to Steve.
All right, I'm Steven Don, and real quick to piggyback off that NGS thing too. NGS's database has gotten so large with all the marks, they're not even accepting new marks anyways. That's why NGS share is really the only way to even get information about a new mark you set on NGS's site. But anyways, types data sets for our GPS are static. The types data sets were raw format at a Rhinex file, a receiver independent, what is it called? 1 second, I got it. receiver independent exchange format, sorry. And then for level data, it was a GSI format, which was converted to a DAT file to be able to be read within that software we're using to adjust. And I'm going to be talking about processing and adjusting the data. So we exported the raw format and uploaded to LGO to convert it to a RINEX, which would be sent out to Opus, since that is probably the easiest way to submit it. It comes right. We can convert it right in LGO and then export it. There's not much to do there. And then digital leveling, like I said, we exported it out of the level as GSI format, converted it to a DAT file, or plan to anyways, because the DAT file is the only file that can be read within StarNet, which is what we were planning to use for our adjustment, but that didn't exactly work out because we were using a lot of SSI's programs and equipment, and the StarNet, they have a lot of work to do, and it was being used at the time. So we ended up using Infinity, which I'll talk about later. But for our Opus solution, we imported the RINEX in LGO. We checked for any ambiguities in the data, like multipath or a loss of satellites, just to make sure the data we were sending to Opus was good and it wouldn't introduce any more error into the results we got from them. So after we sent this out to Opus, well, I guess before we sent it out to Opus, we had to wait a period of time. I believe it's like 7 days before we could send our data we collected to Opus, because we wanted to be able to use the precise ephemeris data from the satellites, which ephemeris data is just information transmitted from the satellites about their location, the health of the satellite, and their orbit. And that data, like for when we observe, that data is not readily available right away. You have to wait, I think it's 7 days for precise ephemeris data to be available for the time of your observation. So we waited, and then we sent it out to Opus, and there's a few different options you have. You can select a manual solution where you get to pick kind of the different stations that are used for Opus to come up with their solution. As our Opus solution was only going to be used as a check, it wasn't going to be used to determine the final values on our control. We just selected the automated solution, which they run a series of checks on these different core stations and things that they're going to be using to derive their solution. And then they pick the best that they see fit and use those. So we select the automated, and then we also selected the extended output solution from Opus. And this is, once again, as we were trying to follow MDOT spec for setting this control as closely as possible. We selected the extended output, and the reason for this is the extended output gives us state plane coordinates, which were going to be the final value types for our control. So we didn't have to convert these into state plane. The extended output gave us an easier way to compare our values to what we got through Opus.
Good.
Yep. And then our manual network adjustments. So once again, per MDOT spec, we have to run both a minimally constrained and a fully constrained adjustment on our network. The minimally constrained adjustment just means you're holding one single point as fixed for your network, and all others within the network are being adjusted to it. So the point we held was PEA, and then we run all our vectors only holding PEA, and all other points are adjusted to that. We good?
Yeah.
All right. And that was once again just used as kind of a blunder detector. Make sure when we run our minimally constrained adjustment, we have no flags or errors for when we run our final fully constrained. And now for our fully constrained, we held both PEA and Spencer, 2 out of the 3 known points within our static network. The only reason we did not hold Shangri-La was, one, because Shangri-La's elevation was only a GPS observed elevation, so we didn't want to hold this and introduce more air into our network than we needed to. So we held it horizontally, but not vertically. And another reason for this was we made a mistake while running this. We forgot to select a receiver type for Shangri-La, which within LGO, you have to select your receiver type. And within the program, it has offsets in it for different receiver types. And then it'll give you your correct elevation down to your point. We forgot to do this, which again was another reason we didn't hold this point. We didn't want to introduce any more air than we needed to into the adjustment. So to get into our adjustment, we first took our full Rhinex files and broke them up into hour files. Pretty much just chopped them up. We took the full 8-hour session and chopped it into 8 one-hour sessions. This gave us the ability to run many more vectors. So, whereas if we just took the observations full 8 hours from each receiver, we'd only be able to run 7 independent vectors, number of observations or stations minus 1. By chopping this up into hour files, we had 7 independent vectors for each hour within that. So you have many more vectors and stuff you can run, which allowed us to run redundant vectors and vectors as checks. Our redundant vectors were run just overlapping in the same direction from one point to another. Our vector checks were run the opposite way to make sure we're getting the right solution. And the way we run our vectors was for the first session, first 8-hour session, we used those 7 to mostly close our figure. We couldn't do it quite fully with just the first 7. We closed our figure, and then each subsequent session and vectors from that we used and focused on like triangular geometry within our network to give us the strongest solution. And finally, as a check, we also ran vectors, which you can see kind of in the lower left corner. That is the big R core stations, the core station on Ferris's campus. We backfed vectors from our network into that core station. We acquired a solution for the core station and then checked it against the published values on NGS's website. And this was done kind of under the direction of our industry advisor, as like this is a good check to see the kind of confidence you have in your network for the people out there using it later on. Good. Yep. And here, this is kind of blocking. All right. Here are the results from our core station check. The differences were 200ths in the northing, about 300ths in the easting, and this really surprised us. The difference we got in elevation was only 0.003.
Yeah, that one. Or go there.
All right. We didn't expect to get that vertically, and I can't even really tell you why we did, other than all the vectors we were running were pretty short, but we were satisfied with that as a check. And then our level adjustment. Like I said, we're planning to use StarNet, which is a program developed specifically for level network adjustments. This program was being used at the time, so we weren't really able to do that. So we elected to run our adjustment in Infinity, which is a lot less user-friendly, I feel. I've used both. It's a lot less user-friendly for a network adjustment, because for each station you want to hold, each point, you have to break that line there, and you're adjusting separate lines throughout. I just feel a lot better running the whole thing as one network and picking your constrained stations within that, but that's not what we were able to do. And like Chad said, we planned on doing this at Ferris. We couldn't do that. So how we did it was on a job. So we chose to hold the NGS stations, of course. We leveled through those. Our first minimally constrained, we just held 2 of those NGS points and adjusted everything to that. After this was done, we made sure we didn't have any red flags or anything like that. We then started adding constrained points to our adjustment. So there's already previously established control and benchmarks out there. We started adding those to our constrained file, holding those, and then adjusting, breaking our lines and adjusting in between those to have a more confident solutions for our points. And here are the specifications we are trying to meet with all our adjustments. The MDOT spec for horizontal, for primary control, we're only allowed 0.05 error in each direction, northing, easting. And then vertically, the misclosure you're allowed per mile is only 0.02, which I'll talk about. We were able to meet both of these specifications. And here are results to show you. Our static GNSS network, our error for northing and easting was only 0.006, which I was surprised by. I thought it was a fluke at first, and then speaking with our industry advisor, it started to make more sense. Our network, compared to MDOT's specifications, come from all their primary control is set along a job corridor, which could stretch miles. And you have very poor geometry as you're going in a straight line all the way down. Our network was in a small area with greater geometry and much shorter baselines, which is why I believe we got such good results. And then for our digital leveling, we're allowed 0.02 per mile of misclosure. Our highest misclosure for any level loop was only 15,000. So we greatly exceeded the expectations of MDOT. And our accuracies per point, I mean, they varied. We didn't really analyze each individual point and report that, but for the most part, it was right around 100, plus or minus 100 for each point. And our traverse misclosure was 1,300 in the northing, 2,500 in easting and 3/10 in elevation for a total closure of 4,100, which, as Chad said, was not what we were expecting to get if we had run it on points that have been static and leveled. But we're coming off something much better and checking into things that have a lot less air in them already. So I think that's about it for me.
So issues encountered. So back when we set the monuments, it was before Christmas break. And as you can see there in the picture to the right, we come back to school to find Ferris grounds crew parked a nice snow pile right on top of one of our monuments. There's Travis digging it out. It's quite the pile of snow. For the mist dig, there was a few points that we had just covered in flags. We had to find a new location for them, which, you know, they come out, had mist dig, set their flags, tell us where the utilities are. So we go out to these locations. Then if we couldn't put the monument there, we, you know, moved our location, call grounds. They had mist dig come back out, you know, do the process all over again until we were in the clear. So that took some time. As far as excavation of the monuments, the ground around Ferris campus seemed to be very clayey. And for the auger, it bounded up a lot. Every few inches we had to pull it out, you know, knock the clay off of it and then go back at it. One near North Hall, I think it's Monument Don, we were digging down and we found what seemed to be an old asphalt road, which the auger didn't like that, which somehow we made it through and went from there. And then obviously, as everybody else's projects have been affected by this COVID-19 pandemic, with the stay-at-home order issued by the Michigan governor, really put a halt to our project for the most part. As you can see here, there's multiple pictures of setting the monuments. We covered them with straw before we left so they can cure and stay warm. And then you can also see the stamping process and all the snow that had to be moved.
Oh, here's our estimated cost for the project, or what it did cost. We had to change this a little bit because I think our numbers were a little low the first time. For reconnaissance and installation of our monuments, we charged $125 an hour. This was a 3-man crew, $3,000. For vertical control, 15 hours at another 125 for 1,500. Static, that was 20 hours at 75, a 2-man crew, 1,500. And then RTK, 3 hours at 75, 225. And then data processing, we have 12 hours budgeted at $60 an hour. And then our profit factor of 3 gave us a total of $22,335. And adding in office administration and licensing, the use of our equipment, and our liability, it gave us a total of $37,335.
We would like to thank, you know, all of our surveying engineering professors and all that were involved in our program. We greatly appreciate you guys. We'd also like to thank John Ellingston. He provided us with the monument caps. He invited all of us to his Opus Projects training course up in the UP, Marquette, I believe. And then he also had tons of knowledge that he, you know, helps out with as far as, you know, what we should shoot for as far as setting a good monument. And then lastly, we'd like to thank our industry advisor, Brett Everett, and Surveying Solutions for lending us their equipment and helping us with planning and all the adjustments. Thank you, guys.